Review video 11, time constant tau for an RC circuit. Here are some calculations involving RC circuits that involve the time constant tau. We often talk about what is happening in a system at specific times, like t0 or t infinity. In an RC circuit, besides those, we might be interested in what is happening at t equals tau, or t equals 2 tau, etc. Calculate what integer number of tau must elapse before we essentially reach t equals infinity, i.e., for us to get above 99% of the way there. The two decimals that you want to keep in mind for the time constant are 0.63 and 0.37. We said in an earlier video that whenever a quantity is changing for an RC circuit, it's going to get 63% of the way to its final destination in that first time constant. Then in the second time constant, it's going to go 63% of the way that remains, etc. In order to get to 99% of the way there, basically what we want to do is we want to say, how many of these does it take to get us to less than 1% left? A quantity will get 63% of the way there in the first time constant. Or another way to say it, if you're thinking of a decaying graph, it will drop to 37% of its initial value in the first time constant. And then it'll drop to 37% of what's left, drop to 37% of what's left. So if you can kind of see that graph in your mind, you can see where this equation comes from. And basically what you need is about 5 time constants in order to get to 99% of the way you are going. You need about 5 time constants. What's the value of tau for this circuit here? Tau is R times C for an RC circuit. So that's going to be 3 ohms times 4 farads, which is 12 seconds, which is quite a long time constant, but that's how you would calculate that. Now we're going to use that picture and we're going to determine all of these quantities listed on the left here at time 0, at 1 time constant, 2 time constants, and then at a time of infinity. And we don't have to fill these in any particular order, but there's the picture, same circuit as we had on the previous page. And we know that the voltage across the capacitor initially is 0. And once this is all charged up, let me close that switch right there. Once this is all charged up, then the voltage across the capacitor will be equal to that of the battery. So that'll be 9 volts. And then in between here, we're going to go 63% of the way there in the first time constant. And then of whatever's left, we're going to go 63% of that by the second time constant. I'm not going to bore you with those calculations. You can stop the video and convince yourself of these numbers. But again, the numbers we're keeping in mind here are 0.63 and 0.37. And we're just using those approximate decimals instead of a more complicated formula because we're trying to get a conceptual idea of what is going on. The voltage across the resistor is going to be equal to the voltage of the battery at that first instant. And at the end, since there's going to be no current going through the resistor, there can't be any voltage difference across it either. So this is a decaying graph. It's going to drop to 37% of its initial value. Then it'll drop another 37% in the second time constant. What we're going to get here is 3.33 volts and then 1.23 volts for the second time constant. The charge on the capacitor, initially there is no charge on the capacitor. I'm not quite sure what we're going to do. We'll fill those in a little bit, right? We don't have to do these in any particular order. What about the current? Well, the current at the end, we start with that. will be 0. All right. Current initially is just going to be that battery and that resistor taken into account, so I think 3 amps. And what's going to happen with this current? It's going to drop, isn't it? And so after one time constant, it will have dropped to 37% of what its original value was, which to 2 decimals, I got to be 1.11 amps. And then in the second time constant, it will have dropped 37% more, like that. What about the power consumed by the resistor? Well, remember that power is I times V. So if we take the current that's going through the resistor multiplied by the voltage across the resistor, initially we are consuming power at the rate of 27 watts for that resistor. And then we need to take 1.11 times 3.33, which I got to be about 3.70 watts. Then we're going to go I times V, and I got about half a watt. And obviously at the end, there's no current going, so no wattage being consumed there. What about Q? Well, let's see. How about at t equals infinity? We recall that the equation for a capacitor is C is equal to Q over V. So that means that Q is equal to C times V. Well, the capacitance is 4 farads, and the voltage at infinity is 9. So 4 times 9 is 36 coulombs, which is a lot. And what do we do in between times? We're going to go 63% of the way in the first time constant, which I got to be 22.68 coulombs. Then we're going to go 63% of the way that's left. That brings us up to 31.07 coulombs. Now what we're going to do is we're going to discharge this capacitor. We're going to take the battery out, and we're going to close the circuit. And what do we know here? Well, can we put any zeros in here? How about at time equals infinity, there's going to be no power consumed by the resistor. There's going to be no current going through the circuit. There's going to be no charge on the capacitor plates. There's going to be no voltage across the resistor, and there's going to be no voltage across the capacitor. So goose eggs all the way down. How about at time 0? The voltage across the capacitor, we charged it up, it was the same as the battery, so that's 9 volts. At the instant of discharge, that entire 9 volts is dropped across the resistor. The amount of charge that was on the plates, we said just a second ago, was 36 coulombs. We just figured that out. Let me pull this page right here and point at it right there, 36 coulombs. So that's what we have there. The current that's going to be going through the circuit is 9 volts divided by 3 ohms, so that's going to be 3 amps. And the power that's going to be consumed by the resistor at that instant is I times V, which is 27 watts. Okay, now some of these numbers are going to be exactly the same. Let's look at the power, for example. You see the other sheet that I've got here? Look at that. Started at 27, ended at 0. So those other two numbers are going to agree as well. 3.70 watts, 0.50 watts. So far, so good. How about the one above that, the current? Same thing. See that? Initially, it started at 3 and ended at 0, and that's what it's doing now. Starting at 3, ending at 0. So these two numbers here, 1.11 and 0.41, are also going to agree. What about the voltage? The voltage in both cases starts at 9, ends at 0. Look what happened in one of the cases for charging. Started at 9, ended at 0, which means these two numbers are still good. 3.33 volts and 1.23 volts. So the only one it looks to me like we have to calculate is this one right here. This is a falling graph. It's going to drop to 37% of its original value. in the first time constant, and I got that to be 13.32 coulombs. Then it's going to drop another 37%, 4.93 coulombs.